Hey everyone, we are going to take a look at a left-hand sum approximation. We're given this function here, which is just a linear function, 6x plus 7, and we're looking at this on the interval from 0 to 4. Now, if I actually were to graph this function over the interval from 0 to 4, we know the y-intercept is 7. The graph of this function would look like, that's when we plug in x as 0, we obviously get 7. Let's say 7 is about here. And the slope is 6, right? 6x mean the slope just means we, go over 1, go up 6, and so on. And by the time we get to 4, 6 times 4 is 24, plus 7 is 31. So we'll approximate 31 up here maybe. This is not necessarily to scale, and that's 4. And so that point there. So here's the graph just on the interval from 0 to 4. Now, what we're going to actually do with this left-hand sum is to approximate the area under this curve, which in this case is just a line. Now, obviously the area under this curve is a trapezoid, or you can think of it as a rectangle and a triangle, and you can find the area of those two shapes very quickly, and you can find the area under the curve, if you will. But again, as the curves get more complicated, then we can't do that, right? So we do want to work through this problem and show you how you use the left-hand sum. We've been doing several with right-hand sums, and then we'll take the limit as n goes to infinity. We're going to find L sub n, right? N subintervals in general. So when we do that, let's just see how things look a little different. Of course, our delta x is the b minus a. This is the interval from a to b. So it's 4 is b, a is 0. And I get 4 over n. That's my delta x, right? That's the width of those n subintervals in this case. Now with left-hand sums, the arbitrary value we're going to take the value of the function at on each subinterval, which we sometimes call the c sub I, is given by this expression. Notice the difference with right-hand sums, it was a plus I times delta x. Notice this will give us the left-hand sums. When I is equal to 1, right, what happens? 1 minus 1 is 0. This whole thing is 0, and I just get a. A is my first left-hand sum, right? If I'm breaking this interval from 0 to 4 into n equally spaced subintervals, my first subinterval would be from 0, which is the value of a, to, this right-hand endpoint. So left-hand endpoint is 0 for the first one, okay? And remember the width of these intervals, these are delta x, all right? The width of these intervals. And so, all right, we break it up. What's the second interval, the left-hand endpoint? Well, it's going to be a when I is 2. I'll get a plus 2 minus 1, 1 delta x, right? I'll get a plus 1 delta x will be right there. I'll be right at that left-hand endpoint. So you see how this formula will generate the left-hand intervals. And then, of course, we're going to take the value of the function at, right, those points. So here's the algebra of it. The c sub I then is a, which of course is 0, I minus 1, delta x we computed here is 4 over n. So this is just I minus 1 times 4 over n. I'll distribute the 4 over n. I get 4i over n minus 4 over n if I just distribute that through the I minus 1. So that's what I'm going to plug in. So here is the formula for the left-hand sum, I equal 1 to n, f of ci, where the ci is now this stuff, right, times delta x. So what is f of ci? Well, if ci is this, I plug that into the function here. It's 6 times the input, 6 times all of this stuff, plus 7. Don't forget the plus 7. That kind of gets dropped out sometimes. It's part of the function. This all in here is the f of ci. Don't forget our delta x. That happens a lot too. The delta x, right, was 4 over n from above. So here I've plugged all the values in. Now I've just got a lot of algebra to do. My first algebra is I'm going to distribute this 6 through here, right, which gives me 6 times 4, 24i over n, 6 times 4, 24 over n. So that minus that. Don't forget the plus 7 still. If I can simplify or combine like terms, I would, but I'm just going to leave it like this. And since I could combine these two, get a common denominator, but I'm not going to do that. I want to keep the I separate. But the 4 over n, I'm going to distribute through. And 4 times 24 is 96i. Notice n times n gives me n squared here. 24 times 4, 96, n times n squared here. And then 7 times 4, 28, and then just one n in the bottom. So there it is. Now I'm going to make use of the linearity, what we call linearity rules for summations, right? Sum of AI plus BI can break up into the individual sums of those. And then if I have a constant multiple, I can pull that constant multiple out. So making repeated application of that, I can break this sum up this way, right? I break it up in the sum of this thing, and the 96 over n squared is a constant multiply. Pull that out, making use of this property right here. Right, so I just have that summation I equal 1 to n of I, and then the summation I equal 1 to n of this thing, plus the summation I equal 1 to n of this thing. Now notice these are constants because I is what's changing here, right? There's no I here, there's no I here. So what are these sums going to be? Well, remember, if I sum I equal 1 to n of a constant, it's just the constant added to itself n times, or n times the constant. So these sums I can evaluate. So let's just look over here, minus just this times n, right? That's the n times c, n times c. Here's the constant 96 over n squared. Same thing here, this times n, right? These summations come out to be this. Now this I, right, summation I equal 1, this is one of the power sums. So you'll have that formula as I've shown you in class on the sheet. And this one we use quite a bit, so you probably might even recognize it right away. But the summation I equal 1 to n is n squared over 2 plus n over 2. I like this form. You can write it as one fraction, obviously, as n squared plus n over 2, and you can do it that way as well. Okay, now just a matter of cleaning this up. I'll distribute the 96 over n squared through these two terms. Notice when I multiply the first two, the n squareds cancel. 96 divided by 2 is 48. Here, 96 divided by 2 is 48. I have an n up top, n squared in the bottom. That leaves an n down below. Here, one n cancels, leaving one n down below. Here, both n's cancel, leaving 28. And I'll just go ahead and combine like terms. 28 plus 48 is 76. 48 over n minus 96 over n, same denominator, 48 minus 96, negative 48 over n. So this is L sub n. Go all the way back to the beginning, right? There's L sub n equals this. And so here's my simplified expression for L sub n. This is for any left-hand sum now, for n equal whatever number, you can write out what it is. So if you want to know what L100 is, what's the left-hand sum where you have 100 subintervals? Well, it's 76 minus 48 over 100. 48 over 100 is 0.48, so 76 minus 0.48, 75.52. That's the value. Bang, or just like that. So very nice. But now what the question is, right? What is the limit as n goes to infinity of this thing, right? Well, just plugging that thing in, we know the 48 over n as n goes to infinity is going to 0 because the n gets bigger and bigger and bigger. Much bigger than the 48, so that ratio is going to 0, and we're left with 76. So there's the answer, 76. So if I go back to this geometric problem now, what is in this case, because this function is above the x-axis, right? If I were to shade in this area here, what is this area here? Answer, 76 square units. 76 square units. Okay, so that's just a little different situation than a right-hand sum. Mostly I'm going to ask you to do right-hand sums, but that's what it would look like with a left-hand sum, and it just adds a little wrinkle with this I minus 1 term in there, makes things a little bit more complicated with the algebra. Okay, hope this helps.